if something's first derivative is not continuous, then it's infinitely not differentiable.
Okay. So then think about a problem that is continuous but not differentiable. Okay, can you have an object, can you have Isaac moving with constant velocity from 0 to 2 seconds?
Well,
With 2 meters per second.
Okay.
Okay, 3 to 4 second Isaac accelerated negative acceleration and negative force.
Okay, so when
No. He's at 4 seconds, his velocity is 0.
Okay, so it kind of plateaus here, which means it probably has a high initial velocity this way, and it goes negative that way. Okay.
Okay, so negative velocity doesn't mean negative acceleration doesn't mean negative velocity as you see that. And negative force doesn't mean positive acceleration as you see that. So from here to here is positive velocity, negative acceleration, negative force. From here to here, negative velocity, negative acceleration, negative force. Okay, so Isaac, first you're going to give us the equation for this. Okay, I'm going to move over there so Isaac can move over there.
Actually, you don't need an equation to show that this is definitely not differentiable, but we can do that anyway. So we'll draw it as a piecewise of three different functions.
Close attention, use the space wisely because we don't have big space.
So firstly, we have from t is between 0 and 2, we have what? 2t. Secondly, we just have 4 from 2 is less than or equal to t is less than 3. Now, you might be asking, why are you putting less than or equal to signs here? And on some, but not others. Well, if there were no less than or equal to signs, it's defined from 0 to t to 2, exclusive. And then it's defined from 2 to t to 3, exclusive. Which would mean that d of 2 would be totally undefined. But we want this to be continuous and defined at every point. Thus, we simply choose to add these signs. But physically, in the exam room, it's not like this is going to be specified. This is just a mathematical basis. So,
okay, this one is a little bit more complicated than the other two.
So, well, what is the pattern of motion that it's following? Well, it's
second degree polynomial.
Yeah. So it starts from t equals 3 though, not t equals 0.
That's right.
Which means that to measure the position over time, we're gonna have to use t minus 3 to make sense of it.
To compensate.
Well, so if we have, well, yeah, think about it. Normally, the function would look something like this, but f of t plus 3 is going to move it all the way over here.
Yes, okay.
Wait, f of t
minus 3.
Yeah.
Squared. Okay, you continue. I'm coming.
So, d of t over this interval is going to be at squared plus bt plus c. Alright, so what do we know about this? Well, I'd rather write, actually, d of t is equal to a t minus 3 squared plus b.
Isaac, I'm going to be back in 2 seconds. You continue, okay?
Plus c. Okay. So, how do we figure out the equation from this? Well, it's simple. We just form a system of equations from plugging in the 3 points that we know. Well, 2 points that we know, because this point right over here gives us no information. So, let's try it. What happens if we plug in d of 3? Well, d of 3 is obviously 4, but I think we should actually approach this another way. This is probably going to be inefficient. let me use the physical equation, di plus vit plus half at squared, because that's what we're going to be applying to these three too. So di is 4, as we know, plus vit, well, we don't know. So I'm going to write p minus 3 plus half a, we don't know, p minus 3 squared. Okay, so if we plug in, well, what can we plug in? D of 3 gives us 4 plus 0 plus 0. So we just get 4 equals 4, so that doesn't give us much info. What if we try D of 4? Well, that gets us what? 4 plus VI plus half A. And what's D of 4? Well, you can tell from the graph that it's 8. And finally, what's D of 5? Well, we know that it just can be 4 plus VI times 2 plus half A times Q squared, which is just 2A. So D of 5 is 4 again, meaning we can cancel these out, and we get VI plus A is equal to 0 after dividing through by 2. So that means we have two equations now, this and this. And in fact, I'm going to subtract 4 from both sides to get this. So now I'm just going to subtract this equation from that equation to get 4 is equal to negative half A, or in other words, A is equal to minus 8, which obviously means from this equation, VI is equal to plus 8. So that means that our formula is just 4 plus VI, which is 8, times T minus 3, plus, well, A is minus 8, so we get this. So this is our final equation in the end. 4 plus 8 times T minus 3 minus 4T minus 3 squared. It's going to take a long time to actually write this out as the quadratic equation on its own, and it's easier to take the derivative this way, so we'll just keep it this way. So 4 plus 8. That's not good. 3 is less than or equal to T is less than 5. Okay, so, God, where's the eraser, man? Where could I possibly left it? Oh, screw it. Guess I'll just use this box of tissues. Yeah, that definitely doesn't make the most satisfactory noise. But hey, what can I do? Alright, so now let's get down to trying to graph V, A, and F. Now, as we know, V of T is
Sorry, I have to help your mother. Where are we?
Graphing V of T.
Oh, so we got the function for 3 to 5 seconds?
Yeah. Okay, so now to actually figure this out.
Baby, can you write the function in the simplest form?
This is basically.
Sure.
Okay, so now we just have to take the derivative. So what's the derivative of 2t? That's just 2.
2.
What's the derivative of 4?
0.
Well, that's just 0. And what's the derivative of this? Well, this goes to 0. This just gives us 8. And this gives us minus 8 times t minus 3. By the chain rule, the derivative of t minus 3 is the same as t. so we don't have to add anything different.
Okay. So
So
let's
then-
take the derivative one more time.
yeah, okay. So then taking the derivative to get a of t, we just get 0 and 0
And negative 8.
from 0 is less than or equal to 2, t is
Maybe
less
don't
than
block
3,
it.
and 8, well, negative 8.
Oh, 0, 0, 0 in the middle. This one is 0.
Yeah, but it's from
Oh, okay,
0
okay,
to
okay, sure,
3, so we combine these two
Yeah.
intervals.
3 to 5.
So we get 3 is less than or equal to t is less than 5. Alright, so what do we get over here? Well,
You go all the way there. Yeah.
v of t, how do we draw this? We have 2 from 0,
0 to 2
2.
second.
then we have 0 from 2 to 3. So you can already see a discontinuity right here. That's why I'll make it look like this.
Okay.
And then we have a jump over here. So it starts from 8, clearly. If we plug in t equals 3 here, we just get 8. So this is not to scale. I can make it to scale.
And we're just going to call it the final velocity 8, right?
Okay, and here it is. So
Good.
here we have 8 and negative 8 and 2.
And we have no. How can we describe or explain this jump between like at 3 seconds there is a jump and at 2 seconds there is a jump?
Well, yeah. I mean, this
Differentiable?
no, this just suddenly comes to a stop. Oh, abruptly comes to a stop. So it starts moving and then it suddenly stops moving. Then it suddenly starts moving again with an even higher velocity. Now, we obviously know this can't happen in real life because it would have to have actually infinite acceleration in these two
To
points.
make it.
Even though our acceleration function doesn't look like that analytically.
So
These kinds of functions can only exist mathematically, and we're trying to apply that to the physical world, but it won't really work because these things can't happen.
can real life can possibly be like this?
Yeah, something like that.
Okay, good.
But this can't happen. You need infinite acceleration, but that conflicts with how things go over here. This can only exist mathematically. There is no concept of what velocity and acceleration means when we put it into this graph. And here,
And can you show how did you get 8? The velocity, final velocity is 8.
I mean, you get 8 minus 8 times t minus 3, then you plug in the beginning of that interval 3, so you get 8 minus 8 times 0.
And
which is
put 5 and then it's negative 8, right?
Yes. So, acceleration over time is very simple, as you can see. Now, obviously, it wouldn't look like that physically. And we're not really doing distance, velocity, and acceleration. We're more doing f, f prime, and f double prime. There's
Okay.
no concept of what acceleration means when we put it into this graph. So, we just have 0 over here. Well, technically a spike here, but that's not included in the math. So, then we have,
No, I think negative acceleration.
oh yeah, over here, which is negative 8, of course.
And by the way, this area will not be the final velocity for obvious reason.
No, specifically because of these jumps right here. If it was continuous, it would work, but it's not continuous.
Okay.
Okay, and finally, F. Well, force just looks like a scaled up version of acceleration, and I don't know the mass, so.
Mass is 10 kilogram.
Okay, well, that's not going to change how I draw it, and I can't draw it to scale, because I mean, 10 times this is the entire length of the chalkboard.
Is it safe to call this as impulse, or that's also problematic?
That's also wrong.
That's also wrong.
Yes.
Why?
Because, I mean, what is impulse? Impulse is the change in momentum, obviously. It's just m delta v. And we already said that the acceleration can't be... Oh, wait, no. Yeah. We already said the acceleration can't be used to dictate the change in velocity over time.
So the final velocity is what? Negative 8? Is the final velocity negative 8?
Yes.
But what is this one area?
Well, this area is negative 16.
Negative 16. If we use Vf is equal to Vi plus At,
Well, okay.
Vi,
Well, yeah. It works if you're on this interval in specific. Because over this interval, it's entirely continuous, and that's physically possible. But if you plug in the whole thing, Vf is negative 8, and Vi is, well, 2 plus At, and...
acceleration minus 8. Oh no, we want to find this one. Not that this one is negative 8. So...
Well, the acceleration isn't even constant the whole time, so... There's the problem.
Okay, oh yeah. Yeah, so but that equation will be able to fix it, right?
Which equation?
This equation, initial velocity is, let's say initial velocity is, I don't know, initial velocity is 2. It's 2 minus 8.
But it's not even 8 the whole time.
That's, okay. Alright.
That's the problem.
Okay. So we cannot call it impulse.
No.
Okay.
I mean, at the end of the day, this is not real. This is not distance. This is not velocity. This is not acceleration, and this is not force.
So why are you using this to show them the a continuous function? You cannot necessarily be able to.
You can't have a non-differentiable function in physics. Well, not in kinematics, at least.
Okay.
Okay.
Alright. So yeah. So show that this is continuous. That's the last thing you're gonna do. This is continuous but not differentiable.
I mean, to show that it's continuous,
I'll use I keep this one. So make a space for you.
okay. So, I mean, to figure out if it's continuous, then all we have to do is show that the limit as t approaches a of d of t is equal to d of a for all a within the domain from 0 to 5. So, how do we show that? Well, over these intervals, in specific, they're all polynomials. They have to be continuous. The only things we're looking at are the little points where they switch right over here. Now, because of the equivalent signs right over here, we know that d of 2 is defined as, well, 4, just plugging in t equals 2 to here, and we know that d of 3 is defined as 4 plus 8 times 3 minus 3 minus 4 times t minus 3 minus 3 squared, which is also equal to 4, actually. So, we know that d of 3 is defined as 4 and d of 2 is defined as 4. So then, I mean, how do we show that the limit as t approaches 2, d of t is equal to d of 2? Well, we have to show that the limit from the left is equal to the limit from the right first. Okay, d of t is equal to the limit from the right. Well, technically this is the limit from the left and this is from the right, but... Okay, so... From the left... Yeah, I'm getting my signs confused. But whatever. So...
From the right...
One side of them is 4, and the other side of them is 2 times 2. So 4 is equal to 2 times 2, obviously. That works out. So we get that both of them are equal to 4, which is also actually the value of d2, which means that this works out. What about the limit from the left of t d of 3, and then the limit from the right of d of 3. Okay, well, from the left, it's just... Well, this way, it's just 4, and this way, however, it's 4 plus 8 times 3 minus 3 plus 4 times 3 minus 3 squared. So this all gets set to 0, of course, because it's 3 minus 3, and we just get 4, which is obviously true, and that's equal to our definition for d of 3 as well. So we know that it's continuous over the exclusive intervals 0 to 2, 2 to 3, and 3 to 5, and we also proved it's continuous at 2 and 3.
Now we're going to prove that it's not differentiable here. This was the greatest video. Probably lots of people don't understand this concept, will understand it.
Now, to show that something isn't differentiable, all you have to show is that its derivative is not continuous at a specific point. So, I mean, for example, if I don't think we have to show this using a formal limit, but obviously, coming from the left, you can show that the limit as t approaches 2 from the left of v of t is equal to 2. But from the right, it's equal to 0. And so, the two different limits aren't equal, which means the actual limit does not exist, which means therefore it cannot be equal to v of 2. So, in other words, the limit doesn't exist, so it can't be.
And that's true also at 3 seconds. If you come from the left,
if you come from the left, it's 0, but if you come from the right, it's 8.
8. So that's not good. So this is not differentiable, it fails. This is also not differentiable.
Well, no, this is not differentiable, this is not differentiable, and this is definitely not differentiable.
As you see the jump, how can you explain that? As you come from this way, the acceleration is 0. If you come from this way, acceleration is negative 8. So limit from right is not equal to limit from left.
Yeah.
So
and same thing with 4.
So the function is continuous, but the function is not differentiable. If this video really help you understand that a function can be continuous, but at the same time simultaneously is fail the differentiability, then let us know if this video really benefits you.